We're going to look at fluids that are in motion. So what we're doing really now is we're taking a look and thinking back to ourselves. We talked about velocity and displacement and that stuff earlier in the year with kinematics. Now we're looking at fluid mechanics. Still mechanics, okay? But we're combining the two things. So a fluid that is moving. We're going to have three major objectives. We're going to discuss the motion of a fluid using what's called the continuity equation. The second objective is to recognize the effect of Bernoulli's principle on fluid motion. And third is to differentiate between turbulent and laminar flow. You've heard the word turbulence before when referring to airplanes and boats, turbulence. And we'll talk about today what creates that turbulence. Okay? Alright, so the first definition we're going to look at is the word laminar. And laminar means, and there's a typo on there, if all points in the fluid flow are on the same smooth, predictable path. So add the word are up here. Okay? If all points in the fluid flow are on the same smooth, predictable path. Okay? Which is opposite of the next term, turbulent. Turbulent has some irregular, unpredictable fluid flow. Okay? You know what I make an analogy to when I think of this? Do you remember rational numbers and irrational numbers? Rational numbers, you could predict the decimals, like 1.5 or 1.33333 repeating. But irrational numbers like pi, there was unpredictable decimals. 3.1415297 goes on and on with some unpredictable values after. So when I think of it like rational and irrational is the same thing, analogous as far as an analogy goes, okay? Tell me you remember. But you could also remember turbulent flow. Turbulence on an airplane, it shakes, right? You can't predict these shakes suddenly on the airplane when the plane starts to rock back and forth. That's turbulence, okay? And we'll talk about how that exists and why it exists. Third term, somebody already said, I've heard viscosity. Viscosity, and this is an easy thing to know, and I'll give you an example of something, but it's the amount of internal friction within a fluid. Think about syrup, maple syrup. It's very thick, right? And it flows very slowly. It's got a very high viscosity. Okay, there's a lot of friction inside of the internal parts of the fluid. And here's an example also. If you're thinking about a river and a river that's flowing, the bottom of the river, that bottom layer of water, has friction against the bottom floor of the river, against the sediments, against the rocks. But the top layer or the middle layers have friction between each other. So the different levels of friction within the fluid change. And in fluid mechanics, one of the courses I took in college, you learn about how it changes as a function of the height. So the fluid that is closer to the bottom floor has more resistance because it's slowing down from the bottom floor of the river. Whereas the top water travels actually a little bit faster. Okay? It changes based on the actual amount of viscosity or the amount of really friction that's going on. So think about fluids as layers of fluids on top of each other. And them moving over one another. So imagine this layer of water over another layer of water. The amount of friction or resistance there, that's what your viscosity is.
For laminar, do you say something is a laminar or it is laminar?
So the flow is laminar. The flow of the fluid is laminar. Or the flow of the fluid is turbulent. Yeah. Okay?
Viscosity is also when, when you go to eye level and you see isn't that it's a meniscus?
Almost.
That's
Yeah, I think of meniscus. Meniscus. That's all right. All right. The fourth thing is the definition of what's called an ideal fluid, which is what we're going to deal with in this class. Remember when we did projectile motion and we said no friction, right? We assumed no friction because it would change the equations up and we would not be able to solve those problems. We're doing the same thing here now. When we study fluids and fluids in motion, we're not going to look at just any fluid.
or when we didn't consider gravity.
Yes, exactly. We're going to look now at what's called an ideal fluid. Something that is incompressible. It cannot be compressed like a gas can. It is non-viscous, meaning no friction, which we've assumed all year. Okay, we've only had a few examples with friction when we looked at our forces. And then the third part, we assume that it is non-turbulent. So these three assumptions are going to hold true for the rest of this lesson. We're going to be considering ideal fluids. If you start looking at what are called non-ideal, or sometimes also known as non-Newtonian fluids exhibit completely different properties than standard basic Newtonian fluids. So we're looking at ideal fluids that are Newtonian in this class. Okay, and if you go on to college, you want to study this, you look at non-Newtonian, and the properties change a lot. Okay, things change dramatically. Let's see. The last thing I want to talk about is something called the Reynolds number. Okay, the Reynolds number. Anybody watch Always Sunny?
Oh, yes.
What's Frank's last name?
Reynolds.
Frank Reynolds, right? In the show. So, this is the analogy. I know it's going to sound weird. But think about Frank's character in Always Sunny. He's Danny DeVito. And he's the one who's kind of crazy sometimes, right? He could be a little bit crazy or a little bit irrational. And before, what did I tell you? Irrational and rational was the difference between terminal and laminar and turbulent. So when I think of Reynolds number is the number that's going to tell us whether it's laminar or turbulent. Okay? So based on the Reynolds number, if it's a low Reynolds number, write this down. A low Reynolds number is indicating laminar flow. A low Reynolds number indicates laminar flow. A high Reynolds number indicates turbulent flow. And there's a breaking point, a boundary. And we don't care what that is for now, because we're not going to calculate Reynolds numbers. But the idea, it's a terminology or a quantity, it's dimensionless, meaning it's got no units, that tells us whether or not something is considered to be laminar or turbulent. It is based on several things. I'm going to show you right now. You don't have to know how to calculate this, but just the idea. The Reynolds number is based on the density, and I'm writing it as I say it, rho, the velocity, and the diameter of the piping system. In this case, it will change if it's not inside of a pipe. It's called the hydraulic diameter, which is something that can change. Don't worry too much about that. The first two are really important. So what these first two say is if there's more density, it's going to be a higher Reynolds number. So things that are more dense have higher Reynolds number. Things that have faster flow have a higher Reynolds number, which makes sense. Faster flow means you'll probably have a turbulent flow, right? A river rushing really fast has a lot of these turbulent flows and these little currents. So that's the higher velocity. This is all over a number called viscosity, which in this case, it looks like friction. Remember friction was mu? Mu in fluids is called viscosity. It's specifically called dynamic viscosity. But viscosity, again, this term that represents the internal friction. And think about this, ready? Molasses has a very high viscosity. A very high viscosity. It flows very slowly. Very slow flow is most likely laminar flow, not turbulent, because it's moving slowly and it's predictable, like syrup again.
Like honey.
Or honey, perfect, like honey. So, if you have high viscosity, it means you have a very high denominator. Take a look here. You have a high denominator if you have a high viscosity. A high denominator means a low number over here. Remember, if you divide by a bigger number, the result is smaller. That's part of math that you learn about indirect. These are indirectly related. If you increase this quantity goes down. So the higher the viscosity, the lower the Reynolds number. And the low Reynolds number indicates laminar flow, which proves to us that things like syrup or honey have a high viscosity and a low Reynolds number. They flow slowly with laminar flow. Okay, Steph?
So if something was had a laminar flow, it would have high viscosity?
It would have a very high viscosity for laminar flow, absolutely. Laminar flow can come from... So laminar flow comes from either low density, low velocity, or high viscosity. And turbulent flow is a result of things that have high density, or high velocity, or very low viscosity. Okay, they're all kind of opposites. What is what? The capital D is the diameter of the piping. Okay, but it's not always inside of a pipe. Fluid flow outside, like over an airplane wing, is not in a pipe, and you have to use a different quantity there. It's called the hydraulic diameter.
Low diameter.
Ignore the diameter. Ignore the diameter part for now. Okay?
P is diameter.
That's not P, guys. What is this? Rho. And rho represents the density. The density.
Are we gonna usually, what kind of like environment are we usually gonna look at? Like, is it typically gonna be a pipe?
Oh, it's both. It's both. In this class, we're going to look at piping, yes.
Yeah, that's what I'm saying.
We're going to look at internal flow mathematically. We'll talk about external flow as well. Okay?
Alright, so you get like, say you have a clog in like your drain or something.
Uh-huh.
That would change all of this?
Sure, that would change the D value.
No, wouldn't that change the mu value, like the bottom
It
part?
would change a lot. It would actually mainly change the D value. The D value is really representing what's called the hydraulic diameter, which is a
Which would be
ratio.
what actually can go through if there's like a clog.
If there's a clog and there's a little opening, this value will change. If there was a clog completely, right, a complete clog, this would become 0. So there would be no Reynolds number because there is no flow. When there's a clog, there's no flow, so you can't give it a Reynolds number.
Okay, so
Okay.
if, say there
Same
was
thing
like
with
a
this.
clog and like a little can go through or something, but it's just going through slower, could it have like the same Reynolds number as say like syrup or like honey?
Sure, it would be slowing down the V value and lowering the
Wait,
D
would it
value.
change the viscosity or just?
The viscosity is a property of the fluid itself.
Oh, okay,
Okay?
yeah.
Viscosity is a property of the fluid.
What is the V stand for?
Velocity. The little v. Okay?
So if like, I don't really understand that, if a fluid is like honey and it's like, where is it getting its internal friction from, like stickiness?
Yeah, the interaction between the layers and the molecules are moving much slower compared to like water. Water which rushes over itself, or oil.
Oh,
Okay? Alright, let's go on to take a look at what's called the continuity. And this is actually quite simple. Okay? Just read the statement to yourself. A fluid flowing in a pipe has a constant, what's called, now this is a term you have to italicize or underline, obviously you can't italicize, volumetric flow rate, which is represented by A times V. What are the units of area?
area, no, meters cubed, no.
Volume is meters cubed. There you go, good Thomas. Area is square meters. Volume is cubic meters. What's the area of the units of velocity?
Meters cubed.
Velocity, not volume. Velocity.
Oh,
Meters per second squared?
Oof, meters per second.
meters per second.
Come on, people. Old school stuff. Acceleration is meters per second squared.
Ah.
What would the units be overall then if you multiplied these? What would the units be?
Meters cubed over second.
Yeah, and take a look. Isn't meter cubed? Is it meter cubed volume?
Yeah.
Per second means a rate always, right? Volumetric flow rate. That's what we're looking at now. Cubic meters, the volume that is past a certain point every given second. And you've seen this before. You talk about like gallons per minute. The amount of gallons per minute in a fluid line that actually transfers. So your washing machine has a certain amount of gallons per minute that come into the lines. A toilet bowl has a certain amount of gallons per flush. Gasoline has a certain amount of miles per gallon. These are ratios. Same thing. So this is the amount of volume, cubic meters, per second that is being moved. So what we can say is that it is a constant. That's the key here. Which means that the amount of volume passing this little opening in the beginning is the same as the amount of volume passing up here. So because of that, we're going to have some interesting facts here to write down.
Can that be changed?
It can be changed, sure, if the volume changes,
No,
but what...
there's like a clog.
Absolutely, Alan. Yeah, we're talking about just a pipe that is flowing through. But you know what's going to change is the velocity, not the volume. So hold on. Let's take a look at an example. Let's say the area of the small opening is 2 square meters, and the velocity coming in is 14 meters per second. Okay? So the area of the opening initially is 2 square meters, and the velocity coming in is 14 meters per second. If now the area at the other end is clearly bigger, right? You see that? It gets bigger for A2. Say the area at the other end is or make it easier, 4 cubic meters. Okay, what would the velocity be? What would the velocity be? Just go ahead, God bless you. Go ahead and plug it in your equation there. Go ahead and plug it in your equation.
Oh, 7.
Sal, can I see your stop
Maybe
for 2
7.
seconds?
7? Oh, sorry.
Plug in.
7? I thought this was like I thought this was just like 7.
You could do it just by looking at it, yeah, and you'll see that, obviously. In a minute, you'll pick up on the pattern or the idea there. So we have, again, it's going to be 2 times 14 equals 4 times whatever the velocity is 2. And as Helen said, it's definitely 7, right? 2 times 14 is 28. 4 times 7 is 28. So what happened here? The area doubled, the velocity what, Chaz?
Well, no,
The area doubled from 2 to 4. The velocity went from 14 to...
20. No,
What was the answer?
wait. 7.
Yeah, so what happened to the velocity?
Half.
It halved, or it got cut in half. Okay? So if the area doubles, the velocity gets cut in half. Think about the reverse of that and make sense of this. The most simplest example for you to think about is this. If you're watering your garden and you have the water flowing out of the garden hose in the backyard, and what happens when you move your thumb over it?
Oh, it comes out so strong in there.
Because the area reduces, right?
Yeah.
Think about it for a second. You take your thumb and you put it over the end of a garden hose. Suddenly the velocity increases dramatically.
So far, yeah.
Because you've decreased the volume. This example here, we increased the volume. And what happened to the velocity? It went down, it decreased. So what we can say is our statement is the following. If the area decreases, the volume increases. Or the velocity increases. Again, if the area decreases, the velocity increases. So how are they related? What's the word that describes their relationship?
Inversely.
Inversely related. They are inversely related.
Why does that happen? Like in the shower,
Mhm.
you know how you can sometimes change like
The setting,
go
yep.
out, yeah. So
It's
like,
changing the cross-sectional area of each of those openings,
But
which
why is
changes
that
the
like a
velocity
thing?
of the water.
why can't they just make the can't they just can't they just push more water into it, or was it?
Sure, but you know what? The water that's coming into your house has a standard pressure that it's pumping at. So they can't change the pressure, which would cause more volumetric flow rate. So instead, they change the cross-sectional area that's opening, which makes it come out faster. And you feel like that, like massage setting or whatever they are, right?
Wait, but
You
what
can
if
change them.
But why is this like a rule? Can't you like adjust this and stuff?
The only thing that you could adjust outside of the cross-sectional area would be the pressure gradient, the
And
amount
what
of
happens if
pressure.
the pipe bursts?
A, it could burst, B, that's A. But B, it's also provided by some standard. You don't change that. It's given to you by the water company. It's a certain amount of flow, a certain amount of time
Is this like
period.
a rule of science?
It's not a rule of science, it's more of like a standardization. Like the amount of electrical current you get is a certain value. Like you get 120 volts or 220 volts depending on the type of outlet. That's a standard.
So this is what we like go by, but it's not actually like that.
It could change depending on where you are, sure. Yeah, absolutely. Absolutely. In a minute, we're going to relate pressure to this whole situation. Okay?
'Cause I'm thinking like, shoot, what's the one like MV1 equals MV2?
Momentum.
Momentum. I'm thinking like momentum is like a rule of science that can never change, but this could change.
Well, this rule will never change, but you could have other factors that also affect the velocity instead of just the cross-sectional area.
Okay.
Okay? For example, if you're pumping from a high height to a low height, gravity speeds it up. So that's a whole other situation. This equation, folks, is a simplified version of an equation you're going to use in calculus and differential equations that relates all of these. And it's a much longer equation called Bernoulli's equation. Okay? And this is a simpler version of that. We're going to look in a minute at what's called Bernoulli's principle. Not the equation, but the principle. Before that, though, let's look at another example, a little bit different. So don't assume the answer you're going to want to assume right away. I'm telling you now. Trust me on this. It's not what you would think it is. It's a common mistake, this question. So we have water is flowing through a pipe that has a radius of 4 centimeters with a velocity of 5 meters per second. What should the radius reduce to for the velocity to double? Don't answer. I'm telling you right now. Do not give an answer right away. If you want to give me givens, that's fine. But if you think you know the answer, I'm guaranteeing you right now it's not right. Okay? I'll tell you now, who knows what the common mistake is that I'm probably thinking of? What do you think it might be?
Measurements. Because
Centimeters.
Okay, fine. Conversion, absolutely. But I'm saying, what is the common mistake as an answer just by inspecting this problem?
That the radius should have.
Yeah, the common mistake would say half. Because you double the velocity. And a minute ago we said if you double the velocity, you have the area. But we're not looking at area. What are we looking at now?
Radius.
And if you remember, area equals pi r squared. So we no longer have some linear relationship. We have r squared, which is nonlinear. So we can't use that rule. Okay? Just to make sure we're clear on that. So we have to solve mathematically. Let's list our givens. What's our givens for this problem? Sibylla.
Velocity was 5 meters.
Good. Initial, or V1, the first velocity is 5.
The radius is 4 centimeters.
Is that R1 or R2?
R1,
Good. And let's convert that.
4 meters.
What is it in meters?
0.04
There you go.
meters.
Okay, 0.04 meters. What else do we know? We know one more thing. Smooth. We know one of these two.
V squared.
V2.
V2 is 2 times 4.
2 times the other velocity.
What? 2 times 5? Oh, it's 2 times 10, yeah.
2 times.
2 times 5.
Which is?
10.
Okay. Again, it's double the initial velocity. That's what we're saying here. So our goal is to find what again? R2. Let's use our words, right? R2 is a subscript. So, continuity equation will be given to you on the test. Okay? But you need to remember the fact that an area of a circle is pi r squared. So you're going to be given this. So this is what you start with. But you have to substitute pi r1 squared and pi r2 squared. Okay? Again, make sure you substitute in the area of a circle. What's on both sides of the equation though? What constant in the front here? The pi. So what do? Yeah, they cancel. It's having a coefficient on both sides. Drop them, please. Which gives us this. Which looks like the continuity equation. Because the continuity equation says AV equals AV. But this is R squared V equals R squared V. So the square is what is making this impossible to solve just by looking at the problem. This is why we needed to go into the math, because you're going to see the answer is not just 2 centimeters. Solve for R2. So divide by V2, and then take the square root. Again, divide by V2 like that. It gets rid of this V2, but then take the square root to get R2 by itself. To get rid of, again, this square term right here. Okay? So, plugging in. Okay, we know their initial radius is 0.04. We're going to have to square that. Times the velocity, which is 5. All over the other velocity, which is 10. Then take the square root of that answer. Okay, go ahead and check on your calculator. Go ahead and check. Make sure you get the right answer. Don't blurt it out. Just write it down for now. I'll write it up in a minute. Go ahead on your own and do this, please.
Wait, how'd you get rid of the V2? I don't get it.
I divided both sides by V2, Helen. Like that.
Yeah.
Which canceled the
Oh, and
V2s.
it's just over there. Oh,
And then I just took the square root of both sides.
Oh, okay.
Oh, because the radius is.
I thought you just got.
Yeah, it's R2 squared. So you got to take the square root. And yeah, I did get rid of the V2 by dividing, though. Okay?
I see what you did there.
So in your calculator you do, yeah.
Wait, so
Hadley? You're going to get an answer of units of meters, right? Because you're looking at a radius. So maybe you should convert that answer to centimeters. Your answer is in... Say again?
Convert it back to 7.
Yeah, just so we have an idea. Let me see your work, though.
I did 0.4 square. Oh.
Yeah, no, the 5's in the... Is he in the exponent? Okay, go fix that.
Wait, Mr. Howell, sorry.
Again, you should be checking. Leave that alone. You should be checking. Nice. What are the units?
Centimeter.
Good. Check your numbers, people. Check your numbers. Be careful. Don't touch them.
Okay, now
Thanks, Mom.
You could get electrocuted.
Thanks, Mom.
Okay, 2.8 there.
I'll write the answer here. Give it to me.
You didn't even do it on your work.
I did it.
So we get an answer in units of meters. Okay, if you wrote it down, I would let you write it, but you didn't have it written down. And you didn't do it. Which is 2.8 in centimeters. So remember the original prediction of 2 centimeters if it were half? Clearly we can see that that was not correct based on this answer.
Clearly.
Clearly.
is it clear?
I think it's pretty clear. Is it clear to you?
Clear, like
All right. 2 more things to talk about, and these are both conceptual. This is the only math part for 9.3. The next 2 things are both conceptual. Okay? This is conceptual, but this was also mathematical.
Well, you
Obviously.
said this is going to be a short lesson.
Okay? It is. We're almost done. These are 2 quick things.
15 minutes.
All right, here we go. Principle is the next thing. Here's what Bernoulli's principle says, and it's very counterintuitive. You would not think this at all, I guarantee you. Okay? And I'll explain why. I'll give you an example of why most people think the opposite. The pressure in a fluid decreases as the velocity increases. So what we're saying is, in this example at the right, P1 is greater than P2. let me explain why I think this is counterintuitive. Show of hands, please. Okay, show of hands. And give your first instinct answer. Okay, so pause writing if you're writing just for a sec, so I want to hear. Show of hands, give your first instinct. Okay, you're back to watering your garden. You take your thumb, put your thumb over the hose. Are you increasing the pressure at the nozzle or decreasing it? Show of hands if you are increasing it. Show of hands if you're decreasing it.
For a second.
Instinct. No stopping. Instinct. Okay. Believe it or not, you guys did well. You're decreasing it.
Well, we
a lot of people think.
opposite.
I know. Yeah. True. But a lot of people would assume right away. You would assume as a little kid that if you put your thumb over the edge, you're increasing the pressure, which is causing it to come out faster, right?
So you basically said whoever raised
But
their hand is a little bit.
What you're doing really is this. You're putting your thumb over the edge of it, which increases the velocity at the spout. Take a look at this diagram here, and I'm going to explain how this works to you. Take a look. Here, we've got some velocity traveling, and the leaf is the model. The leaf is traveling at some velocity through this pipe. It then goes to this little bottleneck, which causes the area to be much smaller, which makes the velocity get bigger. So this velocity is less than this velocity. If there's a change in velocity, what must be present? Think back to Newton. Change in velocity means there is what in the problem? Delta V implies that there must be what?
More time, less time.
You could think of it that way. That is one way of thinking of it. Yes, one way of thinking about it. But what is delta V a result of? There must be something going on.
More distance.
When I drop this pen, it speeds up toward the ground because of what?
Gravity.
Because of gravity, which is what?
Force.
A force. And a force is really a result of what? Or what results from a force?
Mass.
F equals?
M-A-S.
A stands for?
Acceleration.
Remember, acceleration is defined as a change in velocity. So if there's a change in velocity here, which there is, it's speeding up. It means there's an acceleration. Stay with me. Come on, look up. It means there's an acceleration. So again, start with this. Ready? A change in velocity implies there's an acceleration. But an acceleration implies that there is a force. As Helen said, an unbalanced force. But remember, pressure is force over area. So if there's an unbalanced force, there must be an unbalanced pressure or some pressure gradient. So because of this force that's present, it means that there must be a higher pressure here, and a lower pressure here pushing that leaf along. So a higher pressure in a pipe and then a lower pressure in a pipe means that it's accelerating the water or the fluid through the pipe. So this is where the higher pressure is. So when you put your thumb over the nozzle of a hose, what you're doing is you're creating a higher pressure backed up in the hose itself and a low pressure where the water is exiting, which causes it to push and accelerate that water.
Oh, so technically you are increasing pressure, just not.
But not at the nozzle, exactly. Everybody thinks it's a higher pressure at the nozzle.
Confusing me.
Yeah, the higher pressure is backed up in the system, which is
so
pushing it
later on.
along.
Oh, okay.
Okay, it's pushing it along.
So
All right.
that's like with clogs and stuff. The more that like.
Yeah, it's a backup of pressure. A water clog in a pipe is a backup of pressure, and that could cause another burst earlier in the line.
Yeah.
If there's a weakness in the piping, it could cause. Yeah, absolutely.
Can I get a tissue?
All right, last thing. This is an application of Bernoulli's principle. I want somebody to read, and then I'll discuss. Just read it to us nicely. Okay, nice and loud. Chance. Hold on. Start over. Nice and loud.
The force on an airplane wing can be explained using Bernoulli's principle. Airplane wings are designed so that the airspeed above the wing is greater than the airspeed below the wing. As a result, the air pressure above the wing is less than below the wing. The imbalance of pressure creates a net force in the upward direction, known as the lift force.
So what happens is this. You've got a purposely designed airfoil, which is a wing. It's called an airfoil. So that the top of the airfoil,
it's an aircraft.
okay, has a higher velocity than the bottom, and it's made with this shape, okay? So this is a higher velocity. If it's got a higher velocity, as we said a minute ago, it's got a lower pressure. So low pressure up here, high pressure down here, which means that there's got to be a force present. Since the pressure is higher here, it's going to push up. So the force of this is what's giving you lift. That's how airplanes work. There's also something called drag, which is friction. If the lift force can overcome the drag force, you have liftoff. If it doesn't, that plane is not going to lift off. Okay, so the angle of the actual wing, this is a cross section. Here's what a wing looks like, right? On an airplane. Take a cross-sectional cut of this right here. Cut across and look at it from the side. When you do that, what you're actually seeing when you cut from the side, you're seeing is this airfoil right here. That's what you're seeing when you cut across the wing and you look into it. That's the shape of a wing. Okay? It's called an airfoil. It's a wing. It's another word for it. So the idea, I actually don't know the etymology of that word. I'm not sure. But the idea is this again. The shape of it is designed for a reason, so that you create a high pressure below the wing, giving it a force upward, or a lift force, so that the plane actually takes off. Okay, so the plane actually takes off.
You should start with that example, that makes it.
Yeah, but if we didn't talk about pressure and the differential and causing force before, it wouldn't have made as much sense. So I'm leading to it, I know. So it could have gone both ways there, yeah. Okay? All right, your homework for this is only one question. Okay, there was only one applicable problem in your book. Okay, yeah, I'll go back. Just write down this problem first. 337, question 2, part A.